So thank you to LSIC and UTEP for the opportunity to be with you all today. I'll ask you to bear with me a little bit. I've had some allergy issues from Illinois and the dry plain there coming out here. So I might have a little bit of voice dropping out, but thank you for being here. And I'm going to talk today on lunar and terrestrial construction. So I'm going to cover an overview of Caterpillar, give you a little bit of who Caterpillar is, talk about autonomy and terrestrial and mining construction applications. Also talk a little bit on simulation tools that we use for development of terrestrial machines that do these kinds of excavation tasks and some of the benefits of that and applicability from a lunar standpoint. And then we were asked to talk about a few challenges that we might see from the lunar environment aspect. And so I'll cover a couple of those. There are many, many challenges as this community is well aware of, but I'll focus on a couple of those. So a little bit about Caterpillar. I think this community would probably know us well as the world's leader in construction and mining equipment. We also have a whole segment that's focused on energy and transportation. So those are products like that are focused on energy power generation, marine transport, rail, etc. We are a global company. We have over 4 million products at work around the world. We're at about 150 locations worldwide in 25 countries. And we also have about 160 dealers worldwide in 193 countries. So for us to be able to develop and support all of that equipment on a worldwide basis, as you can imagine, we're involved in many technology areas in product development, but there are some specific areas that we're really focused on right now. And those are in the areas of autonomy, connectivity, and electrification, or as we refer to them as the ACE technologies. And all of these technologies by themselves have quite a bit of opportunity for us to be able to provide value to our customers, but it's really in the integration of those technologies and the synergies that they can bring in an integrated fashion where we can really help to solve some key problems for our customers. So I'm going to focus on the first one, primarily in this discussion, on the autonomy area. So we've been involved in autonomy for actually decades now, dates back into the mid 80s where we started work on looking at autonomous mining trucks. About 10 to 15 years ago, we were involved in a program with NASA at Johnson Space Center that focused on remote control technology and automation. In that program, it was the first time that we did long range remote control. So we controlled a Caterpillar platform machine in Peoria, Illinois from Johnson Space Center in Houston, Texas. And that was through what you see on the left hand of this slide, a remote operator center that was developed in that program. Then on the right hand of this slide, you can see what is now the remote operator center that's in production at Caterpillar. And you can hopefully draw or see some of those design concepts and lessons learned from the work that we did with NASA that's now in the production system. So this is an example of our command for dozing, semi-autonomous tractor system that's in production. It utilizes that operator center that you just saw. That center would be located in this specific example about a 10 kilometers from the job site, but it could be 1,000 kilometers. The operator sits at that operator station and supervises 3 to 5 of these dozers doing an overburden removal application. So he will take direct control of the platforms. He'll do a few setup tasks like establishing where this drop-off point is, where they're pushing over the edge, and then assign them their specific task and turn them loose on autonomous operation. And then he will monitor their progress and also be able to take direct control again if they encounter something the autonomy system's not able to handle. and manage that exception control and then turn it back to autonomous operation. So an example of that could be, a poor blast of the rock, and you get a large boulder in the area that they're trying to doze. He'll take direct control, he'll deal with that, and then turn it back over to autonomous control. So we also have in production the command for hauling product. So this is Autonomy on large mining trucks. It's been in production for a little over 9 years. We now have over 560 trucks operating worldwide at 24 different customer sites. And over that time period, you can see we have accumulated nearly 200 million kilometers traveled autonomously. So that's a number that, we all drive, or most of us do. And I think we can all get an understanding of that's a very significant number of kilometers. But we've also moved 5.1 billion tons of material autonomously. So to put that into perspective, that is the equivalent of more than the construction of 500 Hoover dams. It's also, if you think about a 4-lane wide highway, 6 feet deep, all the way around the circumference of the world, it's equivalent to that amount of material. So very, very significant amount of material that has been moved autonomously. And through all of those, the development of all those stats, the operation of this over this 9-year period, that's all been done with 0 lost time injuries from a safety standpoint. So what I just, described to you and showed to you relative to mining applications and some of the autonomy kind of systems that are in production, those are what we would refer to as first generation autonomy. We're now working on next generation autonomy that we refer to as One Autonomy. This is intended to be a scalable type of an architecture that allows us to be able to apply autonomy more easily across the wide range of different platform types of machines that we have. And of course, we serve multiple industries, namely mining and construction in this area. They use it, and certainly our dealers as they are equipment and those systems. So this is an example of a use case relative to this new architectural development and the focus in the construction area. So this is in the area of solar farm construction. So when it comes to the solar panels themselves, they are typically brought into a central location on the site in a staging area, and then they're in boxes on a pallet, and a machine like you see in the picture here, which is a compact track loader, is used to pick up the pallet and then take it out and deliver it to specific locations throughout the solar farm area to be then installed. So this system is looking at a semi-autonomous kind of approach, very similar to the dozer approach that we just showed you in mining, where an operator would have, through a tablet type of an interface, the ability to drive the machine directly, pick up one of these pallets, give it the specific location at the site where that pallet needs to go, and assign that task to the platform. It would then autonomously traverse to that location, drop off the pallet, and then return autonomous back to the staging area. He would then take direct control again and pick up another pallet, give it an assignment, and send it on its way again. And by doing that, we would be able to effectively manage or supervise 3 to 5 of these platforms performing that construction application. So this is an example of some of the simulation capability that we have at Caterpillar that is proprietary to Caterpillar. The ability to model machine and machine systems and the dynamics of the machine, but also the ground itself and the machine's interaction with the ground. So in the in the background, you see the actual wheel loader platform running, and in the foreground, you see the digital representation of that same platform. And so these are all physics-based type of simulations to represent the machine and the ground. And then we're also marrying to that proprietary capability, also simulation capability relative to autonomy and autonomy development as well. So we can look at the entire aspect of the platform and its development, including autonomy. And the reason why we do that, and this is why it's, I think, relevant to you all in this community as well, is that, you know, we can't represent everything we need to in physical test, either because of being able to just construct the physical test and or because of the cost of that. And I think that's certainly true for all of you as you look at the lunar applications, as well as many of the aspects of the lunar environment are going to be difficult to represent all of that in physical test here terrestrially. So the ability to do that in the simulated world as well will likely be very important. And then in terms of some challenges, so as I mentioned before, I mean, there's many challenges involved with trying to do these things on the lunar surface, but I'm just going to talk about a couple of them. So from an autonomy standpoint, everything that I've showed you today, the successes that we've had in this area of autonomy, that autonomy is all built on machine platforms that are very mature. So those machines or their configurations have been in production literally for decades. Now we're constantly making, you know, updates to those, enhancements to them, but the general type of machine and its configuration has been out there in use for decades. And the application and the environment in which they are used in has been known and understood, and, you know, we've been involved in for decades as well. And we're putting autonomy on top of that. And that is hard. It's a lot of work, it's a lot of effort, it's very difficult. I mean, this community is now going to be faced with that same trying to do autonomy, but on platforms that are going to be brand new in an environment that is still a lot to be understood, probably especially from the aspect of what it means to do true excavation tasks in, and so on. So it's a really large challenge. Another area is equipment wear. I think I've heard that brought up a little bit, maintainability and so on, that's being looked at, which is great to see that the community is focused on that. So equipment wear is an area that we certainly deal with terrestrially all the time. If you look at this photograph of this bucket, you can see all the way across the front of there are teeth, and then between each of those teeth are small or segments, cutting edge segments as well. All of those parts we refer to as GET, or ground engaging tools. They're all designed to be replaced, to be serviced, because they wear. And in the mining industry especially, it's very common that they are looking at replacing those on a weekly basis. And in extreme situations in mining, it could be every 24 to 48 hours. Now, I don't know that you're going to face the same level of loading and the kind of cycles that we're facing in our equipment to drive that kind of a wear rate, but wear is going to happen. What the pace of that wear is going to be in your environment, what are your trade-offs of the ways to deal with that based on all the other constraints that you have in terms of, do you have labor local to be able to deal with it? How much material can you bring from Earth? All those things will be, I think, an important and a challenging thing to be factored in what you're looking at and doing. And so with that, I think Rachel, are we going to do a few questions then? Or is that your just sub panel? Sure. All right, well, thank you.